And today's speaker is Mykola Vovchanskii with the talk devoted to uh, I think, multidimensional finite point densities for Arratia flows with drift. Please.
Thank you. The object we are discussing is very standard. We have a Brownian wave that is a family of coalescing linear processes that move independently before they meet and then just merge without changing their velocity, that is their variance. And we consider a situation where there's an extension of this notion where
Excuse me, did you say something?
No, I'm getting some request remote control, and I think someone is just pressing the wrong button.
Mhm.
We have a situation, we consider an extension of that notion where we have not just linear processes, but linear processes with drift. So every particle in our system satisfies a stochastic differential equation of this type. So this is our particle, this is our linear process. And for every point of start in time and space, there is a separate linear process. So today's talk is actually a short one, and it will go as follows. I will recall what our so-called endpoint densities are, and we will discuss a result approximation theorem for them. Since I've already discussed a version of the theorem for the Arratia flow, the Brownian web without drift, and I also discussed some ideas in the case where drift is present, I will only very briefly recall the idea and the proof. And I will explain why my idea that I was talking about in spring didn't work. However, I will explain an alternative route, and for that we will discuss representation of these densities as some series of iterated integrals, essentially via means of perturbation theory, and I will explain why it works and how to prove this representation. This latter part is an extension of the work that was done by myself, Professor Drogovtsev, in a paper in one-dimensional case. So very quickly, let us recall what endpoint densities are. Essentially, there are two main ways to introduce them. The first one goes to physics, very old. So this is just such functions that the integral on the left side of the expression can be represented as an integral with respect to this function, to this density. Another interpretation, this is almost the Radon-Nikodym density of factorial moments of the corresponding point process, because in the Arratia flow, as we know, there is only a finite number of particles that survived after a finite amount of time has passed. An alternative definition, we can consider the number of particles that got into this interval and consider such almost derivative of this expression. Now, it is sufficient to assume that A is just bounded, and then we can prove that such densities exist. An alternative proof can be found in this paper under slightly different assumptions. I will also say that sometimes if what follows, we consider not densities for the whole flow, but densities for the flow that start from some bounded interval of the real line. But all the results of its existence are essentially the same. So this might be some interval. I will need to recall the following notions, that if we have a system of coalescing processes with no triple collisions, which is true for the Brownian wave because because of the Crisanov theorem, essentially. Then we can introduce some encoding to remember which particles meet first and which meet later. So there are obviously a number of ways to do this. For instance, we can just look at the first collision and remember the number of the particles that is started higher. So this is one particle. Then we enumerate them from scratch, and then we find another second collision, and we remember number 2, because this is the particles participated in the collision and started higher than the previous one. We do not care about precise times. We will say that this encoding is a coalescence scheme. And then we can slightly modify the notion of the endpoint density, in the sense that we can introduce densities that correspond to the finite number of starting points. So here we consider not the whole flow, but just a part of the flow. The start of the point U1, UN, U. And we can add additional condition that precisely that the coalescence scheme that is observed is precisely as small. This is just an indicator that allows us to write the sum. Without this, this is 0, essentially. And obviously these densities are well related. And some of the results that will be formulated later can be reformulated in the cases where A is not just bounded or continuous, but also continuous, or just bounded but has just continuous but with linear growth. Now, my talk contains 2 main results. The first result is as follows. If we consider a partition of the interval from 0 to 1, or from 0 to, say, u, it doesn't matter, and consider the flow that starts from this partition, we can recover the density for the whole flow that starts from the whole interval by considering this density. So these are points of our partition, and we can catch the speed of convergence, which is always the same, and we can also find the value of the constant that stands here, in the sense that essentially no collision should happen. And if you consider this partition U1, U2, etc., such intervals should hit in between of these points. Since I already discussed the idea of the proof a number of times, I will go quite briefly. So what we need this one-sided interval, b plus epsilon of y. We need nt of a, this is the number of particles that hit this interval when started from the whole line, or more precisely 0, 1. I'm sorry, it should be 0, 1. And if nt has 2 arguments, that means that we start from B and hit into A. And instead of considering this sum directly, I will consider this expression. And it's quite easy to show that this is actually related not to the number of particles hitting these one-sided intervals, but to events that we have at least one particle. So we need to calculate the difference of the probability that there is a particle when started from the whole flow in every such interval, minus the probability that this happens when we start from our partition. And this is our error. Essentially, this means that we start from something like U1, u2, u3. Here lies our b plus epsilon y, some y. And we know that there is a particle from the original flow that doesn't start from the partition that hits this interval, but at the same time, no particle that from partition hits this interval. So they should move in such a way that they hit lower than this b plus epsilon y. And in the terms of the dual flow, that essentially means that we need to consider flow that starts from these ends of this interval and misses particles of our partition. Particles that start from the original partition. There is a result of a recent result that states that the dual flow for the flow with drift A is still Brownian web, the Arratia flow, but with drift minus A. So the next step of the proof is essentially that this expression that we defined on the previous slide, this is I, can be replaced with the sum that stays in the limit from something that disappears. So essentially, we want to get rid from 1 minus m squared, where 1 over m is the size of the partition. While we also need to care about this epsilon. So how to do this? Let us introduce additional point y epsilon. So this is while epsilon takes y from Rn and gets to R to n by adding to the every second coordinate epsilon, and let A be the event that particles that start from these ends of this interval and essentially move backward in time do not coalesce. And then to prove the lemma, we need to remove, to estimate expression of this type. So this event holds, this event happens, and also pairs of particles either hit simultaneously some interval, maybe with coalescence, maybe without coalescence, or they hit two intervals, like in this case. So this pair hits one interval, this pair hits another interval. Sorry, they start from B plus but hit U1, U2, UK2, UK1. We are moving backward in time. And to do this, let us introduce the set of all coalescence schemes that allow only the collisions with. And if we to consider the probability that we want to get rid, for instance, this type, we can estimate it from above by using the n2n density that correspond to a specific coalescence scheme and is integrated with respect to two such intervals. Now, here stands our x epsilon. This should be y epsilon. And The idea that works very well in the case where drift is absent is to write this formula in the terms of the Karen-McGregor determinants, which is the density of the Brownian motion with no drift, conditioned, not conditioned, that suffers no coalescence, essentially. So this is this determinant where G, just a Gaussian density with variance T at point Y, G minus X key. So there is a lot known about such determinants. We discussed quite a few things. In particular, it has nice estimates in terms of the Morda determinants, like this. So it has a Gaussian part, essentially. A van der Waals determinant, H and X, is a sum over A less than Y, X, Y minus X, G. And here stands some polynomial. Here given a description of this polynomial, but we don't care about specific description. We know that this is a polynomial with finite number of terms. In case someone is interested, one of the previous talks that I gave on the seminar contains a lot of information about this and where to read proper information. So if drift is absent, we can actually write down a system of iterated Cauchy problems with shrinking dimensions, and we can obtain this representation for our endpoint density. Now, if we want now to integrate this with respect to two intervals of size delta, we also got very good part here, because here is going to stand x equal y epsilon, and this y epsilon will give us exactly epsilon in power n, which allows us to get rid of this supremum when estimating the remainder in this expression. And we also got this expression too. Obviously, when drift is present, this doesn't work because this is still a fundamental solution of the corresponding equation. This is still some good expression, but it doesn't allow us such nice estimates in terms of this epsilon. And my original idea that I hoped to achieve was as follows, that if you consider just a Wiener process, W, we can decompose it as a value of this Wiener process at terminal time t plus Brownian bridge eta. Then we can introduce meeting times for the original process, W, in the way that W goes to coalescing version W hat. And we can introduce additional constructions that correspond to coalescence and just Brownian bridges from U to Y. And then using the special Girsonov theorem for the Arratia flow with drift proved by Professor Drogovtsev, we can introduce such expressions where essentially we remove those parts of W that are not preserved by the coalescence. Because we know that the two particles coalescence, one particle dies. So here, these parts are removed in this expression. So this integral from 0 to t, but essentially this is only to this moment of time. And there is a way to rewrite the original meeting times for W in terms of these Brownian bridges. And one important feature of this decomposition is these two Gaussian variables are independent. And then there is another alternative. We can take our n-dimensional density and get another representation alternative to the one discussed previously, in the terms of just Gaussian densities, integrals with respect to Gaussian densities. And this function that is essentially the corresponding exponential from this version of Girsanov's theorem for the Brownian web, but conditioned by this expression. So here is a formal exposition what is this, but it doesn't really matter. We just choose particles that have survived. This is a subset of particles that have survived. There are chi surviving particles. We choose G because we are interested in G point density here, and choose all combinations and integrate over all other particles. And obviously it doesn't help us. However, my initial idea was that we can obtain, and I still think this is possible, but I don't know how to do this, and I will explain in a moment why, that we can obtain a very similar decomposition where here stands the Carlian-Magrevo determinant. So essentially, and instead of taking instead of considering this exponential, which is a function of W and our Brownian bridge, and conditioning it on the values of Wiener process at the terminal moment of time, we must consider coalescing versions and consider this expression. And we don't need much. Obviously, disintegration doesn't happen anymore because we cannot conclude that these are independent random variables, random elements. But still, one can expect that this is a nice function. For instance, this is bounded in a proper sense that it can be integrated with respect to the Gaussian density continuous function. And I will just say like 2 or 3 sentences that because disintegration doesn't happen, I try to do discretization of the integrals. And because then we can use some Markov properties, we can replace this expression with some integrals over discretized versions, which look like good functions. But the problem is that I still do not know how to prove that the limit of such functions is what we need, unfortunately. I still think that this should be possible in general, but as of now, I ran out of ideas. So, unfortunately. However, the theorem that we described in the very beginning still holds because we can go via a different route. So let's discuss a representation of endpoint densities as series. And then using it, we can not only establish the representation, which is of separate interest, but also we can prove the theorem at the beginning. So again, this is a development of the result that was established for one-dimensional densities earlier. So let us introduce such integral, such differential operator. Here, simplex of size 2n. It's parts of its boundary in a very simple part. So, and the corresponding operator of taking normal derivative is very simple in this case. And again, we consider it all coalescent schemes that were of importance for us to simplify the expression. And for every such scheme, we can define some boundary condition, which is just a sum of indicator of this hyperplane, which means that we want some coalescence to happen, which means we control where they should hit. And then let us consider this differential equation, the Cauchy problem. We start from 0. We want to hit in proper places, and we do not want to hit wrong hyperplanes, and we want it to solve this differential equation in a weak sense, minus because we are working with the dual flow. And there is a separate result that now it is sufficient that function is just bounded. It doesn't need to be continuous. Then the endpoint density can be obtained as essentially a special derivative of the solution of that equation in this way. So we need take derivatives, half of first derivatives, and we need to calculate it in a proper point. Then this function is good inside. It can be once differentiated once. And this is a weak solution to the original Cauchy problem. And what is most important, it can be written as a series. And so formally, if we start looking for a solution, it obviously should be of this form. So this is our right-hand side, so our source. This is double layer potential that corresponds to the boundary condition, and this is just the part that corresponds to the initial condition. And now we can iterate this expression starting from the first step of this form, and we arrive at the following expression. So the first term, this term is exactly the term that appears in one-dimensional case in our previous work. And note that we have here one derivative, and here stands exactly what we need. Here is the determinant of Carlin-McGregor, and we have here just Carlin-McGregor determinant. And here we have a slightly different expression that is different in the sense that there is one additional operation. We take first derivative of the double layer potential. Now I will skip details how this works and why this works actually. But I will explain what was the problem and how to solve it. So if you look just at this expression and assume for a moment that we don't have the Carlin-McGregor determinant, but there's the Gaussian density, then the expression, the integral from 0 to t ds, some part of the boundary, I don't care which this part is precisely, the sigma y, the mu y, gt minus x, y, and want to estimate it using something from straightforward parametrics method, you will arrive at the conclusion that because our boundary is very good, that is Holder continuous even better, this can be estimated as t to some lambda greater to less than 1, tn plus 1, t1 half, because we are taking one derivative, but we are smoothing by using this operator. And this holds for good boundaries. And here goes essentially t minus s, t minus s, t minus. And unfortunately, if we just use this very standard estimate, because we also have additional derivative here, essentially dx k for some k, this doesn't work because lambda, which appears because mu y has something, etc. Doesn't allow us to integrate. So you need to go a little further in the sense that you need to consult results on smoothing properties of double layer potential. And one good reference is Vovchanskii, Uraltseva, works of Kaminin from 60s, and very recent results by Luzini and his co-authors, in which a number of results about such double layer potential is established, in the sense that they are mostly formulated in the sense that if the density of the double layer potential belongs to some Holder class, that it actually goes up in terms of smoothness. And we know that this integral is differentiable, it's quite differentiable for good densities, because it's solution of the corresponding heat equation. And using those calculation in repeating them, because unfortunately you cannot just take any specific reference from here. One of the closest one is Vovchanskii, Uraltseva. They consider the situation where the boundary is just a hyperplane. So they are working with half spaces. But still, you need to do some work and just repeat those calculations to conclude that this is a good integral. It allows good estimates. It's actually sometimes it's even bounded, etc. I will skip those calculations because I don't think they bring anything new. And also, I have an idea to maybe revisit such calculations one day, because obviously you are not limited to only simplex and equation for coalescing Brownian processes in the simplex. You can also consider more general domains, and that can be interesting because you can discuss some functionals of related to coalescing Brownian motions in terms of such representation, where you can get of drift, for instance, and then theoretically it can give us some results on direct representation or maybe other formulas for analogs of the Carlin-McGregor determinant in case drift is present, because the only case where the corresponding Carlin-McGregor determinant is known when drift is just linear. Then there is a direct formula by some harmonic transformation. So maybe this adds some points. However, as I say, even though it looks bad, it requires some calculations, this doesn't essentially add any problems to our picture. So essentially the proof after you're done with this calculation goes almost exactly as the case of original paper. I will very quickly just recall the proof to explain how it works. In the original paper, we had simpler time because we can just use Gaussian estimates, and we have very good quick estimates for our derivatives of our terms in our series. Though here we at one point get something like 1 over s plus 1 over s squared. However, the standard idea is to consider, to prove this, and then to go to the limit in the space of Schwarz distributions to conclude that this works in a weak sense. And for that, one should use this representation, because this is how series are essentially built. And one has this. This should be here. It's funny because exactly the previous talk of Alexei also made correction in the last moment, and that backfired. This is controllable, so we just consider the difference that corresponds to the first derivative, test it with a compactly supported function, and do some calculation. You need to prove that something is uniformly continuous. I will not repeat those calculations from the paper. Some terms can be treated via probabilistic method, in the sense that you need to consider some stochastic differential equation where drift acts coordinate-wise. So A is just a collection. A of x is just ax1, ax2, etc. And then some terms that you need to work with can be actually rewritten can be rewritten in terms of essentially the original function, where we substitute R, your process, and have indicators that something doesn't happen. And here you can use Girsanov theorem to prove the corresponding convergence, exactly in the previous paper. And to finish the proof, you need to prove that the series you obtained has a probabilistic interpretation, which is an interesting question, because since we are working with infinite domains, theoretically, the initial Cauchy problem may have many solutions. But it's done exactly in a very standard way, multiplication procedure. If drift is very good, the corresponding operator is hyperelliptic, the corresponding series is a smooth function. And then, again, this is a part of folklore, in the sense that we had to write down explicit calculation for this in our paper, but I can obtain this. Now we have smooth functions that approach our A, and using the Girsanov theory, we can rewrite it in terms of the Brownian process without drift, and some stochastic exponential, the Dolander-de exponential, and go to the limit. Essentially, we need to prove these two limits and to prove that series are also convergent, and this exactly can be done at previous paper. So as a result, now, because the expression we obtain contains the Carlin-MacGregor determinant, we can go back to the first theorem and finish its proof. And also, exactly in the original publication devoted to this series representation in terms of series, we have convergence of endpoint densities when drifts are convergent, say in L infinity, L1, etc. What I would love to do with this representation, to do some explicit calculation, but as of now, I don't really know. So there are very natural candidates as something that pushes particles towards one specific point like zeros, but it's not clear how to approach it as of now. And this part I already told about. So essentially, this is all I wanted to tell you today.
Okay, thank you very much for interesting talk. And maybe somebody have questions or comments, please. So as far as I understood, the last theorem was not proved or proved.
Proved.
This statement proved, yeah?
Yeah, yeah.
Okay.
We have two main results: series representation and
And this one, yeah?
yes.
I see, I see. Okay. Interesting.
Yeah, I was very disappointed that I couldn't finish what I hoped with this alternative probabilistic proof.
But why not now, when you have the result, now came back and try to understand what happened with this representation, yeah?
Yeah, so obviously this is the last part. The last time I was speaking about this approximation, but maybe I will return to this representation one more time.
Yeah, it seems to me that if you now have a proof that it can be watched, that everything is good, then maybe some compactness argument can help that you will see that this Schumann also have some limits and so on.
Yes, probably. Because this is actually one of the problems I met. I couldn't prove that this discretized version satisfies some conditions of Arcello's Colli theorem. I cannot
Yes,
control.
exactly. Yeah, it is interesting. Okay, thank you very much. And now we just have to ask Georgi who is the next speaker for the next week.
I will be the next week.
Oh, okay. Very good. Then you will announce yourself.
Yes.
Okay, nice. So for today, that's all. Thanks, everybody, and bye.
Goodbye, everyone.